You ever just look at your closet and wonder about that explosion of color? I mean, from deep blues to these super vibrant reds, our clothes are basically a canvas for chemical art. But how does that color actually get there? And maybe more importantly, how does it stay there? Well, let's dive into the pretty amazing science behind the colors we wear every single day.
It seems so simple, doesn't it? But the journey a single color molecule takes from a vat of liquid into the very core of a fabric fiber, well, it's a fascinating bit of chemistry. So together, we are going to pull back the curtain on that entire process.
Here's the game plan. We'll start with the chemical messengers that actually create color. Then, we're going to follow a dye molecule on its journey into the fabric. After that, we'll get into the wild science of why we even see color in the first place. And finally, we'll uncover the secrets to making that color last.
Okay, so before we can even think about dyeing something, we need to understand the substances that are doing all the heavy lifting. It all boils down to two key players, dyes and pigments.
First up, we've got the dye. Think of it like a colored chemical that's meant to be absorbed. The key word here is soluble. It dissolves in something like water. This allows it to get inside a material and form a real chemical bond, becoming a permanent part of the fiber itself.
A pigment, on the other hand, is pretty much the total opposite. It's insoluble, so it doesn't dissolve. Instead of becoming part of the material, it's more like a superfine powder that just coats the surface, and it needs a binder to hold it in place, kind of like the clear stuff in paint that holds the color.
You know, here's probably the easiest way to think about it. A dye is like a stain. It soaks in and becomes one with the fabric. A pigment? That's like paint. It's just a layer sitting right on the surface.
This table lays it all out perfectly. Dyes are usually soluble, organic, and they diffuse into the fabric. Pigments, the opposite. They're insoluble, often inorganic, and they need that binder to sit on top. This one difference is why dyeing your t-shirt is a totally different chemical ballgame than painting your wall.
Okay, so we've got it. A dye needs to get inside the fiber. But how in the world does a tiny soluble dye molecule actually make that trip from the water and then lock itself in for good?
Let's set the scene here. I want you to imagine one single textile fiber just floating in a solution we call a dye bath. Now, this bath is absolutely jam-packed with countless little dye molecules. The entire goal of this whole process is to somehow coax those molecules out of the water and get them into that fiber.
And believe me, it is not just one simple step. It's a whole journey with multiple stages. This flowchart here gives us the full roadmap, showing how that molecule goes from just floating around to being permanently stuck inside the fiber. So, let's break it down.
All right, here are those 6 stages in action. First, you've got diffusion. The dye molecules have to move through the water to get close to the fiber. Then comes attraction, which pulls them right to the fiber's surface. Next is adsorption, where they actually land and stick. After that, they penetrate, going deep inside the fiber. And finally, fixation. This is the crucial chemical reaction that locks them in place. And boom, you've got a permanent bond.
So the dye is locked in tight, but that brings up another huge question. Why does a red dye molecule look red to us and a blue one look blue? The answer is all about how these molecules play with light.
First thing we have to get our heads around is that dyed objects work completely differently than light itself. With light, like you see on the left, when you add the primary colors together, you get white. That's called additive color. But with dyes and pigments, it's subtractive. They absorb certain wavelengths of light. So when you mix them, they absorb more and more light, until eventually, you get black.
So what part of the dye molecule is actually doing all this light-absorbing work? Well, it comes down to a very specific component. And this quote gets right to the heart of it. Color happens because of an interaction between something called a chromophore group and light.
A chromophore, it literally means color bearer in Greek. How perfect is that? It's basically the engine of color inside the dye molecule. Its special structure is tuned to absorb some wavelengths of light and reflect others. And the light it reflects back to our eyes, that's the color we end up seeing.
But the chromophore rarely works alone. It's usually got a little helper, a sidekick, called an auxochrome, which means to increase color. Now, it can't make color by itself, but when it attaches to the chromophore, it can totally crank up the final result, making a color deeper, brighter, or even shifting it a little bit.
So when you put those two together, the chromophore and its partner, the auxochrome, you get the complete color-producing system. And that's known as a chromogen. It's this full molecular team working together that gives us the rich, final color we see on our clothes.
Okay, we've created the color, we've locked it into the fabric, but now we get to the part that really matters to all of us, right? How do you make sure that color stays put through all the washing, the sunlight, and just everyday life?
The industry term for this is color fastness. And really, it's just a way to measure how well a fabric holds onto its color. We've all seen bad color fastness in action. You know, that new red sock that turns your entire load of laundry a lovely shade of pink. Yep, that's a color fastness failure.
And it's not just about one thing either. Manufacturers have to test for all kinds of conditions. How well does the color handle being washed or being out in the sun? What about rubbing against other fabrics? They even test for things like sweat, dry cleaning, and seawater. Every single one is its own unique chemical challenge. In fact, when a company is choosing a dye, they're balancing at least 8 major factors. It is not just about getting that perfect shade of blue. They have to think about the cost, the environmental impact, how it's applied, and of course, all those different fastness ratings. It is a really complex chemical puzzle.
So from a single molecule just floating in water to a complex chromogen locked deep inside a fiber, that is the hidden science hanging in your closet. It's a journey of diffusion, attraction, and chemical bonds. So the next time you pull on a colorful shirt, maybe you won't just see a color, but you'll see the incredible molecular journey that brought it to you.